All right. So, Chapter 7. I really hope you've looked at the video the last couple of... I guess I started... Did I start 7 with you guys on Tuesday? Or not? I can't remember. No, nobody knows. Okay, that's a good sign. Chapter 7 are substitution reactions and elimination reactions. The tricky bit to this chapter is not any one of those reactions by themselves. So in Chapter 8, the reactions are like you have an alkene, and then you have some reagent, and you get a product. And you generally get a product. Like whatever the reagents are, it's going to give you one thing. All right, so I'm not suggesting it was easy. Like that's new stuff, and you got to keep a bunch of different things in memory. But if you successfully do that, if you successfully put those reactions in memory, then right, I've got cyclohexene, I've got H3O+, I'm going to get cyclohexanol. Like that's all you're going to get. The tricky bit to Chapter 7, so we've got substitution reactions and elimination reactions. Forget the tricky bit for a minute. The substitution reaction, one group substitutes in for another, okay? So the reactions are called nucleophilic substitutions, and that means that the thing that's coming in to do the substituting is a nucleophile. All right, so there are a lot of different kinds of substitution reactions. You'll see some others in Orgo 2. In Orgo 1, the only substitution reactions we look at are nucleophilic substitutions. And as I said on Thursday, it's an organic chemistry class. I'm an organic chemist. We focus on the organic stuff. All right? There's, as you'll see this week, you're doing an SN2 reaction in lab this week. There's a bunch of inorganic stuff you put in. All right? You don't really worry about that so much. You're going to view this reaction from the perspective of the organic molecules. All right? So here, the thing that's driving the reaction is the nucleophile. All right? So a nucleophile, and I've also put base here. It's a thing with electrons. So nucleophile is maybe a newish word to you. It's just a Lewis base. All right? It's something that has electrons. And just like we did in Chapter 3, you can have strong acids, you can have strong bases, you can have good nucleophiles, and you can have weak nucleophiles. All right, so in a nucleophilic substitution, our Lewis base is going to bring the electrons in, and it's going to substitute for something that we're going to call a leaving group. All right, this leaving group, chloride, this is the easiest thing. The leaving group is the easiest thing to memorize here. All right, the leaving group is going to be chloride, bromide, iodide, or a sulfonate ester, an O- bonded to an SO2. That's pretty much it for this chapter, okay? So the leaving group has to be a weak base. And if you think about that, the leaving group has to be a weak base. And so if you think about this in terms of an acid-base reaction, right, one group comes in and substitutes for another group, the equilibrium is going to lie toward the side that has the weaker acid or base. Okay, so this nucleophile is a base. So the thing driving the reaction is a base. It's going to kick out another base, which has to be a weak base. Right? So the nucleophile can be a strong base, it could be a weak base, it could be a moderate base. We're going to dig into that a lot more. But anyway, nucleophile, Lewis base, substitutes for a leaving group. That's a substitution reaction. The elimination reaction, the thing that has electrons, again, it's a Lewis base, right? But it's acting as a Bronsted base here. It's going to grab a proton, and it's going to grab what we call a beta proton. So we're going to define the carbon that has the leaving group as an alpha carbon. Any carbon bonded to the alpha carbon is then a beta carbon, right? So any alpha carbon can have up to 3 beta carbons. All right, so in the elimination reaction, the base is going to take the hydrogen from the beta carbon, and we're going to end up with an alkene, a carbon-carbon double bond. And again, the leaving group leaves. So elimination reactions in chapter 7 are all going to give an alkene. All right, so like I said, the tricky bit here, if you look at this, both the substitution and the elimination reactions have a base and a carbon bonded to a leaving group, and that carbon-leaving group bond breaks. They all have that. So the tricky bit in chapter 7 is figuring out which of the 4 possible reaction types happens. We have 2 flavors of substitution. We have 2 flavors of elimination. And we designate them based on rate. If you haven't watched Thursday's lecture, I go into rates and stuff there. I'll do it a little bit here, but that's where you want to see this. So the rate law for a reaction, and hopefully you guys, even though we haven't done a lot of kinetics in here, hopefully you've seen a little bit of kinetics. You can always describe a reaction rate based on some reaction rate constant K, little k. This changes for every reaction. All right, this K changes for every set of reagents. So it's a constant, but it's only a constant when the reagent is X and the other reagent is Y and the solvent is Z and the temperature is whatever, right? Okay, so in Sn1 and E1, that is nucleophilic substitution or elimination unimolecular, right, that one, the rate law only depends on the electrophile or the compound that's got the leaving group. All right, that's where the 1 comes from. The 1 comes from the fact that there's only 1 molecule in the rate law. We also have bimolecular versions, Sn2 and E2. Nucleophilic substitution, bimolecular, so the 2 represents bimolecular. Elimination, bimolecular. And that rate law is going to, again, have some other little k, but the rate will depend on both the concentration of the nucleophile and the concentration of the electrophile. We'll go through some of that in a minute. I guess I'll put up some other stuff here. So Sn1, bless you. So in an Sn1 or an E1 reaction, the carbocation that is formed has to be stable. Tertiary, resonance stabilized, something like that. We'll go into details on that in a minute. The other thing that needs to be true is that the nucleophile or the base needs to be weak. All right. Actually, hang on. Don't write that down. All right, so for E2 and Sn2, the base, the nucleophile, needs to be strong. And that's a necessary thing. So if you have a strong nucleophile, or if you have a strong base, good nucleophile, the reaction will either be Sn2 or E2. And then for Sn2 reactions only, the leaving group needs to be on a primary or a secondary carbon. Go ahead and write that down now. We'll talk about why here in a bit. So those are those are general rules. Another thing that's useful to look at and have some understanding of, you might bring it to class, you may bring it up on your computer if you have it. There's a flow chart in the Chapter 7 module. All right, it's a very useful flow chart. It's the way you ought to think about these problems. Okay, so I'm gonna, crap, I always do this. I should put that on here. And there's no good way of doing this. All right, so I've got I'm just going to put it all the way down. All right. So I've got 4 reactions shown, 1 in each panel. Again, right, like they all look really similar. Secondary bromide, water and hydroxide, and then products. So what I want you to do first in each panel is it a substitution or elimination reaction? And then once you have that, do you think it's, if you've decided it's a substitution reaction, do you think it's SN1 or SN2? If it's an elimination reaction, is it E1 or E2? And then, so mark that down, then I'll put up answers. You guys at home can fast forward if you want. Work the problem. So SN1, SN2, E1, E2, that's 4 reactions. There's 1 of each up here. All right, I'm going to go through and tell you if it's substitution or elimination, and then give you another minute or two to think about which type. The left 2 reactions are substitutions, right? So the leaving group here is going to be bromide. It would have been nice if I could have left this board up. I guess I could have done that much, right? A leaving group is going to be Cl minus, Br minus, I minus, or a sulfonate ester, sulfonate anion. So Br is a leaving group. That means that carbon is the electrophilic carbon. Right? And it's a secondary. So it's a secondary bromide. Basically, this is easy. The carbon that's got the bromide, count the other carbons on it. If there's 1, it's primary. If there's 2, it's secondary. If there's 3, it's tertiary. And OH substitutes. All right, so you don't have hydroxide in this reaction, right? So what is the base / nucleophile? There's only one other reagent. It's water, okay? We'll go through the mechanisms here in a minute. So this is a substitution reaction. Water is the nucleophile. Down below, this is also a substitution reaction, right? Still a secondary halide. Same organic substrate in both reactions. Now, what is the base or nucleophile? hydroxide. So now you've got two choices. You've got hydroxide and you've got water. Why do we know it's hydroxide? Hydroxide is a stronger base than water. Okay? So hydroxide is our base/nucleophile. And that means water is just a solvent. Water is not doing anything directly in this reaction. It is just solvating all the reagents. One sec. Up here, water is both a solvent, that is, it's solvating the substrate and the products, but it's also a reagent. Yes, Rob.
For the hydroxide in the top one, is that like just a regular line?
Yep.
Okay.
Yeah, that's a regular line. I started to draw it as a squiggle. Thought better of it. So if you see a regular line like that, like the hybridization of that carbon that's got the OH is sp3. There's an H on it. There's 4 things on it. That OH is either front or back. When I draw a plain line like that, I'm saying it's 50-50 front and back. Down on the bottom, I'm clearly saying this hydroxide, this OH is back. All right, so these are both substitution reactions. These are both elimination reactions. So again, bromide is the leaving group, same substrate. It's a secondary bromide. Again, water up here is the base/nucleophile. Down here, hydroxide is the base/nucleophile. I did this in chapter 3, but you know, hardly anyone learns something permanently the first time. Like if you think about everything you've learned in your life, how to put a shirt on, tie your shoes, find your way home, like you don't just like, when you were 3 or 2, I don't know how, it's been a long time. I don't remember how old I was when I learned to tie my shoe. But it's not like mom came in, showed me how to tie my shoe, and it was, okay, good, I got it, right? Like you've got to tie your shoe a whole bunch of times, and now you don't think about it. So in any system, if something's going to be a base, the thing that's going to be a base is the strongest base that's present. If something's going to be an acid, the thing that's going to be the acid is the strongest acid present. Okay, so it is really important you can gauge acid-base strength. We did that on exam 2. There was a problem where you had to rank acid-base strength. Very few people got 10 out of 10 on that, so everybody needs to work on that a little bit. Some of you need to work on it more. But that will feed directly into helping you on exam 3. So not only is it important for the final and Orgo 2 and biochemistry and so on and so forth, it's important for this exam as well. All right, so if you've got hydroxide in water and something needs to be a base, it's going to be hydroxide. Something needs to be an acid, it's going to be water. Water is a stronger acid than hydroxide. How did I know these two reactions are elimination reactions? Like without, let's say I didn't figure out the left 2 were substitutions. You get alkenes, right? So we take our organic thing and we get alkenes. So if you have this, if you have a carbon on a leaving, or sorry, if you have a leaving group on a carbon, you have some sort of base some sort of base. Could be a weak base, could be a strong base, and the product is an alkene. It's going to be an elimination reaction. And I've got 3 different alkenes. All right, so we've got trans 2, cis 2, and 1. So these are butenes, right? So trans 2-butene, cis 2-butene, and 1-butene. 1-butene is a constitutional isomer of trans 2 and cis 2. What's the relationship of trans 2 and cis 2? I heard them all, I think. Wow, that was they are not conformers. The double bond's rigid. All right, they would be conformers. It's a good review. So if this bond in the middle was a single bond, there would be free rotation around that bond, and they would be conformers. That double bond is rigid. At room temperature, under normal conditions, not even room temperature, at very high temperatures, under normal conditions, that double bond is rigid. There's no rotation. All right, so the molecule's actually held this way. Cis-trans relationships, are always diastereomers. All the lights are on as high as they go. All right. And in fact, in this reaction, you will tend to see all of these. All right. The major product in an elimination is usually the most stable. Usually it's doing a lot of work here. There is an exception. I'm not going to tell you what the exception is right now, but we'll come back to it. There's an exception in E2 cases. All right, so both of these are elimination reactions. All right, we take a carbon with a leaving group, and we get a double bond, an alkene between the alpha and the beta carbons. All right, if we look at that, right, so the alpha carbon's the carbon with the bromide. We have 2 beta carbons. In all 3 of those alkenes, the double bond, the new pi bond is between the alpha and the beta. All right, take 60 seconds and see if you can figure out which ones. So these are going to be E1 and E2, one or the other. And on the left, one or the other is going to be E1 and E2. Or sorry, Sn1 and Sn2. So see if you can figure that out. Question? Okay. Okay, so right now, I have not really given you enough information to definitively nail this down. I have given you quite a bit. Sn2 and E2 require a strong base or a good nucleophile. You can also call it a good base and or a strong nucleophile, good and strong. I tend to use strong base and good nucleophile. There are molecules that are good nucleophiles without being particularly strong bases. But generally speaking, anything that's a strong base is going to be a good nucleophile, and the stronger the base it is, the better nucleophile. And that's really the one. So everything else pretty much stays the same. We can do Sn2 because the leaving group is on a secondary carbon. Right? If the leaving group had been on a tertiary carbon, we couldn't do an Sn2. That's a good thing to memorize. We'll go through the mechanism here in just a minute, but that's important. All right. So the cases that have a strong base or good nucleophile are going to be Sn2 or E2. So as we look at this, I mean, we've already kind of answered this. The base up here is water. Water is not a strong base. All right? You guys know this. Again, I'm going to hammer this all the time. You drink water. You do not drink strong bases. Right? Strong bases will kill you, like painfully and quickly. Those two usually don't go together, but they do here. You don't drink, like, I don't know, every now and then, if you read poison control statistics, like Drano is a real common household hazard. Drano is like super concentrated sodium hydroxide. Little kid gets into it, drinks it, death. All right, don't drink strong bases. One, that's a PSA, but it's also a way to think about this, okay? Water alone is not a strong base. Hydroxide is. So you've got a strong base in this one. So this is going to be the SN2. The one up here is going to be an SN1. Same thing when we go over here. The one that's got a strong base is going to be an E2. The one that doesn't have a strong base is an E1. So you do actually have enough information to do that. You don't have enough information for my next question. Which of these happens? Right? They all four, certainly you can, so now they're not identical. So the one below, the SN2 and the E2 don't have the same conditions. They have a strong base there. Right? But the two on the bottom and the two on the top have the same conditions. So we've got a secondary bromide, we've got 2-bromobutane and water. We've got 2-bromobutane and water. So do we get SN1 or do we get E1? And the answer is you don't really know. Okay, so what you would need here is a temperature. All right, this equation that I've written up a few times, for any reaction or any process, anything that's an equilibrium process, conformational change, a chemical reaction, a phase change, all of that, the Gibbs free energy of the process is equal to the change in enthalpy minus the temperature times the change in entropy. All right, delta H is pretty much looking at bond strength. And again, all these reactions really, delta H is favorable. The carbon-bromide bond is weak. Well, the carbon-bromide bond is weaker than the carbon-oxygen bond. And you can think about that. So the organic substrate is more stable on the right. All right. So over here, we make a pi bond. But elimination, so delta H is not quite as favorable for the elimination as it is for the substitution. But entropy goes way up, right? We take 2 molecules and we turn them into like 5. Disorder increases a lot. So delta S favors the elimination reaction. So as the temperature goes up, we tend to get more elimination. So higher temperature tends to favor elimination over substitution. So what's a very logical question to ask me now? And there's a lot, I guess. When, yeah, at what, like at 39 degrees, it's all SN1, and at 41 degrees, it's all E1. That would be really nice. That would be lovely. Doesn't work that way, all right? I can't tell you, and I also can't tell you for every substrate, 40 is a high temperature or 40 is a low temperature. I would like to. It would probably ease your understanding of this material. But this is really what I want you to focus on. As the temperature increases, you tend to get more elimination than you tend to get more elimination as the temperature increases. Or conversely, as the temperature decreases, you get more substitution. For E1 and SN1 especially, you almost always see all of them. All right? Practically speaking, in the lab, E1 and SN1 are not great reactions. I know we did a lab a couple of weeks ago where you did SN1, and it was really the only product. Probably wasn't the only product, but the major product was SN1. There was probably some E1 in there. As you look at reactions, you can't really just say, for a new reaction, if I only give you like one temperature, and you have to choose what's the major product, really it doesn't make any sense to say there's a line. But, because I'm going to ask you questions like that, the line is 50 degrees. All right? What I'm not going to do, actually, is ever ask you 50 degrees. Look at the numbers I chose here. 5 degrees? Why didn't I choose 0 degrees? Yeah, it's water, and I would like, you know, as a solvent, you'd like the solvent to be liquid. At 0 degrees, water is going to freeze. So basically, if I want the substitution reaction, I'm doing the reaction as cold a temperature as I possibly can. Okay, E1, I've chosen 100 degrees. Right? If I want elimination, I don't want to do 50 and be like, okay, that's good enough. It's going to favor elimination. I want to just fry the thing. Okay, so if you want elimination, go as high as you can. If you want substitution, go as low as you can. Now, obviously, reactions, pretty much every reaction goes slower as you lower the temperature. So it may turn out that this reaction takes, 3 weeks at 5 degrees. I'm impatient. I don't want to wait 3 weeks. So even though I get a little more elimination, I do the reaction at 20 degrees instead of 5 degrees. Because then it goes in a day. I get like 10% elimination, but I get the reaction done with. So it's a good question. It's an instinctive question. What is the temperature at which elimination becomes more common than substitution? And the fact simply is it depends on the molecules involved. All right? But if I give you a reaction and it's above 50, feel free to consider it hot. If it's below 50, feel free to consider it cold. Okay, the same is true on SN2 and E2. The difference is SN2 and E2 are both intrinsically faster than SN1 and E1. We're going to go through mechanisms here in just a second, and you'll see why that is. But SN2 and E2 and again, these are not like laws of the universe, so there's a usually there. But it gives us something you can hang your hat on for this class. Again, this is not 100% of the time, but in this class, it's going to be 100% of the time. For questions I asked you. If an SN2 or an E2 is possible, that's what happens. Really what that means is if you have a good base or a good nucleophile, it's going to be SN2 or E2. All right? So on the two reactions on the bottom, we have hydroxide. Hydroxide is a strong base. Immediately, you don't have to even worry about is it a good nucleophile. If you have a strong base, you're doing at least E2. If it's a good nucleophile, you're doing at least SN2. In this case, it's both. Okay, so I am going to draw the mechanism now. Okay, so I'm going to do the SN2 mechanism. There you go. That's all. All right, the hydroxide, and that explains our bonds. You've got to make a bond between the carbon with the electrophilic carbon and the oxygen have to make a bond. That bond is formed by the oxygen using a lone pair, slamming into that electrophilic carbon, forming a CO bond. The carbon can't have 5 bonds, so the bromide leaves. Okay, so this long and winding arrow forms the OC bond. The little curved arrow here breaks the CBr bond. And the bromide takes the electrons with it. Now, if we think about that, all right, so there's our carbon-bromide bond. That's a sigma bond. So how many sigma antibonding orbitals are there? Got an answer in the back. A shy answer. Yeah, 1. Every bond has an antibonding orbital corresponding to it. Right? Remember, electrons can only go into orbitals. So when I say this oxygen gives this carbon electrons, it doesn't just leave it on the porch somewhere. It has to put them into an orbital. And the orbital it goes in is the antibonding orbital. All right? And that antibonding orbital is in the same line as the bonding orbital, is the sigma bond. So the sigma bonding orbital's inside the C and Br, the antibonding orbital's on the outside. And what this means is the nucleophile, right, those electrons are in a lone pair there. So the electrons that make this bond have to come from directly opposite the bromine. That puts electrons into the CBr antibonding orbital. If I put electrons into an antibonding orbital, I break the bond. Right? We also call this a backside attack because it's got to come from directly behind it. And this explains the stereochemistry. All right, so the bromide, I've drawn in all of these products. I've shown you one enantiomer. I've shown the bromide out. That's going to be 1, 2. It's going to be an R. I've shown the R configuration for every bromide on the board. All right, when the hydroxide comes from opposite that, for this, it's got to come from the back. So the hydroxide's got to end up back. Backside attack inverts the stereochemistry on right? The stereochemistry on that carbon that's got the leaving group inverts. So if it was pure R, I would get a pure S alcohol. If it was 80% R, I would get 80% S alcohol, right? I'm going to let that sit with you for a minute. Also, my tea's getting cold. We need a microwave in here. Okay, so this is a hallmark of an SN2 reaction, he says pointedly to the people who have lab after this. All right, so if you see an inversion, that tells you it's an SN2 reaction. So you'll see this in some of the old exams. I'm probably pretty soon just going to put all the old exams I have up. That includes exams 2 and 3. Like I said last time, right? Like, there's a lot of crossover. So a lot of the SN2, a lot of the substitution elimination chemistry on old exams is going to be on exams 2. All right, but if I ask you, if I give you a reaction like this and I show the stereochemistry, and I ask you what the mechanism is, there's 2 ways for you to figure it out. Well, 3 ways. You can look at the reagents. This is the less reliable way and the hardest for you. Right? If I just give you reagents, you have to figure out, like, what kind of leaving group do I have? Do I have a leaving group? What kind of base or nucleophile do I have? And based on that, you have to sort of judge, is this, like pretty much the thing I did with you already. Is it going to be substitution or elimination? If it's substitution, is it SN1 or SN2? But I can do 2 other things that really nail it down. If I show stereochemistry like this, and the stereochemistry inverts, that is, leaving group's forward, then it goes back, or the leaving group is back, then it goes forward, or it was left, then it goes right, that's an SN2 reaction. In SN1, the chiral center is racemized. All right, so we start off pure R. We end up with a racemic mixture, 50% R, 50% S. We'll go through the mechanism in a minute to see why that works. But if you see racemized carbon of the leaving group, that means it's an SN1 reaction. All right, what's the other way I can tell? What other piece of information could I give you that would definitively tell you if it's SN1 or SN2? not temperature, but
You get like a strong acid as a product.
yeah, that's not it.
If the hydroxide is a good nucleophile.
So that's the first kind, right? Like that, you're really looking at the nucleophile or the base. If it's a good nucleophile or a strong base, it's probably SN2, not SN1. Yep. The rate law. Remember, the 1 and the 2, that refers to the rate law. So if I give you the rate law, I've told you. So down here, the rate of this reaction would be, again, some K. Don't worry about what the K is. It's K. That would be the rate law. For an SN2 reaction, the rate is dependent on both the concentration of the nucleophile and the concentration of the electrophile. You guys are writing stuff down. I'm going to double check I actually said record this. I did. That would have sucked. All right. So the reason the rate law for an SN2 is bimolecular, again, this is a definitional thing. If there are 2 components in the rate law, it's an SN2 reaction. Well, if it's an SN reaction and there are 2 components in the rate law, it's an SN2. All right. This is a one-step reaction. This is the whole mechanism is a single elementary step. The hydroxide slams into the electrophilic carbon. Carbon-leaving group bond breaks. One step. In the class on Thursday, I told everyone that every elementary step involves the 2 things. So if it's a single-step reaction, you can think about this like an acid-base reaction, right? If I have hydroxide and HCl, the rate of that reaction is some reaction rate constant K times the concentration of hydroxide times the concentration of HCl, because it's a single step. When you have multiple steps, it gets a lot more complicated. Okay? But for an SN2 reaction, the rate law has both reagents in there. And if you think about this practically, what drives the reaction is the negative oxygen colliding with the electrophilic carbon. Okay? Trying to think about, COVID has pretty much destroyed all my SN2 analogies. All right, but if you just think about, like, if we just said, what is the rate at which people collide in this room? Okay, it's lower than before COVID. There are 26, 25 of you in here, 26 of you in here right now. All right, before COVID, there would probably have been, there's 45 in the class, so we'd have like 40 people in here. The more people that we pack into this room, the greater the chance 2 people are going to collide, right? The more people we pack into the room, the greater the chance somebody's going to inhale a virus. That might be, that's painful to think about. Sorry. It is, yeah. So basically, everything about the last year has been kinetics. All right, so as the concentration of hydroxide goes up, the odds of a collision with the alkyl bromide goes up with it. Right? So if I double the concentration of hydroxide, I double the chances that a hydroxide is going to slam into that carbon. And I should say here, for those interested, this K basically represents a whole bunch of factors. It represents the actual geometry. How hard is it for the hydroxide to meet that carbon? Right? The harder it is, the lower K is. The easier it is, the higher K is. It represents how strong is this bond. Right? The weaker that bond is, the higher K is. So that K really encompasses a whole bunch of stuff. It's fun to look at K. You'll do that in physical chemistry if you're interested. But the same thing, it's a one-step reaction. So if I increase the concentration of the alkyl bromide, I also increase the chances that the 2 molecules collide. All right, so if we come over here to the E2 reaction, how many steps do you think are involved in this reaction? 1. It is the E2 and the SN2 are going to be a concerted reaction. There's a single step. And this is a point that raises some confusion sometimes with students. The E2 has 1 step. The E1 has 2 or 3. All right, so the 1 and the 2 do not refer to how many steps in the mechanism. That will be an easy thing for you to think at 2 a.m. a week from now when you're going back over this. All right, 1 and 2 refers to the rate law, not the number of steps. Let's see if you guys can figure out the I'll give you a completely unfair question. All right, maybe it's fair if you've read through it. Draw the mechanism for this one-step reaction, the E2 over there at the bottom. It's not completely unfair, it's just kind of unfair. So as you're going through it, it's one step. So every bond that is formed needs an arrow. Every bond that breaks needs an arrow. Oh, crap. And your instructor really should have written the correct thing on the board. There's no H3O+. If that irritates you, sorry. 45 minutes of that on the board. Wow, all recorded. So that was, if I know you're still working on this, I'm really kicking myself about that. I had a really egregious error here. All right, I drew H3O+ as a product. The sorry, and I've done it again. 45 minutes in and I'm flustered. So H3O+ is a byproduct on the top reaction. All right, but that reaction's run in water. The alkyl bromide itself is a Lewis acid. So you can have an acid. In the bottom reaction, we've got hydroxide, all right? A reaction involving hydroxide is not going to produce H3O+. So your mechanism, I'll go ahead and draw your mechanism. You're going to get water out of it. So the hydroxide, we need to remove one beta hydrogen. We need to make a pi bond. We need to break the carbon bromide bond. All right, so O minus is going to grab a beta hydrogen. That's the proton transfer of the acid-base reaction. The electrons in the CH bond are going to make our pi bond. All right, and then that, sorry.
Does it matter which H?
Yes, kind of. I will come back to that. Actually, no. If you feel like the lecture has sort of gotten away from me, you're correct. All right, so it does, and I'll talk about it in a minute. I didn't tell you which product over here, so in the mechanism you drew, it does not matter which H you grabbed. You could have grabbed either of these, or you could have grabbed that one, right? Any of the three on this beta carbon. If you grab any of these, you get one butene. Now, this H will lead to one of the two alkenes, and the other one will lead to the other one. And that's sort of a stereochemistry thing, like the inversion that I'll come back to in a minute. All right, so O makes a bond to H. The CH electrons make the pi bond. Carbon-bromide bond breaks. The electrons go on the bromide. All right, so it's one step. The rate law is actually the same as for the SN2 reaction, but actually that K is going to be different. All right, so the rate of substitution is different than the rate constant for substitution is different than the rate constant for elimination. But it's a single-step reaction. It's bimolecular rate law. So kinetics and stereochemistry are two really powerful ways to study the mechanism of a reaction. If you want to find out how the reaction's happening, then you measure how the kinetics vary by concentration, and you look at the stereochemistry. So I'm going to put this here. The question came up, does it matter which hydrogen you grab? See if you guys remember this. What you have to do to figure out which hydrogen leads to which product is draw a Newman projection. Good, I heard some grumbling. You'll recall this from back in the winter. So as you look at this, let's tell you what, while I do it, try to draw the Newman projection looking down this bond. All right, that's what I get. Like I said, I'm having a rough few minutes here in class, so that could be wrong. Good, a few people are telling me it's all right. I'm not the only one in the room wrong. That's the one you don't want. So just like over here in SN2, so SN2 and E2 are a one-step reaction, but they're constrained stereochemically. I'll do the E1 and SN1 mechanisms here in just a second, and you'll see how different they are. SN1 and E1 have a much more loose mechanism. In SN2, the nucleophile has to come from directly opposite the leaving group in a backside attack, and that inverts, right? So you can imagine three groups here in the carbide sort of stick on the carbon coming this way. It sort of inverts like an umbrella caught in the wind. Over here, the stereochemical requirement is that the hydrogen that gets grabbed has to be anti to the leaving group. For exactly the same, it's a little harder to imagine it at this point, but for the same reason that the leaving group, or sorry, the nucleophile has to come opposite the leaving group in an SN2, the base has to grab an anti-proton in the E2. And this is the exception I put in up here. Okay, bless you. Okay, so now you'll notice I drew the arrow to here. And I was thinking that that was going to take us to the green arrow here takes us to the trans alkene. If I grab that H, the back H, in this conformation, I'm going to get the trans double bond, right? Because these two methyls are anti to one another. It's one-step reaction, so that whole thing collapses down into an alkene, and there's no time to rotate around that bond. By the same token, I can't grab this H, so let's do A and B, right? If I grab A, I get this one. Okay, to take HB off instead of HA, I would have to go from a different conformation. Right? The back carbon would have to rotate so that HB was here, HA would be there, the methyl would be here. The two methyls would be gauche. And so now when I pull that H off, it collapses down and the two methyls are on the same side. So I'd have a cis alkene. Again, if I grab one of the H's from the methyl carbon, I get 1-butene. Any of the three of them, there's no stereochemistry in 1-butene. So grabbing any of the three of those H's gets me the same one. And like I said, you might think there's just layer after layer. So I'm going pretty deep here. We'll come back and look at some of this stuff. Like, which one of these is major? Generally, again, the most stable alkene is going to be the major product. That is always true on the top in an E1 reaction. The E1 will always give you the most stable alkene. Generally, on the bottom, that is also true. All right, however, if you use a really big base, and I mean this in terms of steric size, right? I'm this big, lumbering, enormous base, and I want to grab a proton. It's going to be easier for me to get one of these protons on the methyl, there's not as much around it, as it would be to get in here and get one of the CH2s. And so we have terms. I'm going to write them up here. I kind of hate to. We'll see how much E2 we get into down the road. But you should at least know these terms. The more stable, the more substituted alkenes are referred to as the Zaitsev products. Again, old Russian guy. The Zaitsev alkenes are always the more stable alkenes. And in fact, between these, the trans disubstituted is going to be more stable than the cis disubstituted. Right, those methyls, for the same reason that the anti-configuration conformation is more stable than the gauche. The Hoffman product is always the less substituted alkene. Okay, and it arises only when you use a really big base. So, you know, there's a lot of complexity there. There is a lot of stuff I just dropped on you. I hope you wrote it down. You can go back and review the tape. It's not really a tape. It's a tiny little disk. But you can review that. We'll talk about it more. So I'm hoping either by Thursday or by next week, I can just come in here. What we're going to do is start working practical problems. I come in and I give you a bunch of molecules and reagents, and we try to predict the product. All right, I'm just trying to review them now. So let's leave E2 then, okay? SN2 and E2 are concerted. They have a bimolecular rate law, a single-step mechanism. There's stereochemical requirements for it, right? E2, we have to abstract a proton anti to the leaving group. In the SN2, the nucleophile has to do a backside attack on the electrophilic carbon. Actually, I do want to throw one more thing in the SN2. SN2 cannot happen on a tertiary carbon. All right, so in the SN2 reaction, let's say we have, nobody's going to be able to read that. I don't know why I think you guys can read that. Not only am I closer, it's like in my mind organized a different way. All right. So if this carbon's tertiary, right, so it's got 3 different groups coming off of it. The orbital requirements are still the same. The nucleophile has to hit that antibonding orbital. But now there's all this stuff. There's all this molecular structure around that antibonding orbital. So the nucleophile can't access this structure. The same way over here, like a really big base is going to prefer to grab the less hindered proton. In an SN2, the more hindered the carbon with the leaving group is, the slower it reacts. Tertiary carbons won't react at all. Secondary carbons, like this one, react fairly slowly. If that methyl wasn't here, right, it would be a primary bromide. That would react faster. And if it was a methyl, it would react fastest of all. All right? All right. Take a deep breath. And actually, this HBr is H3O plus Br. All right, so how many steps do you think will happen in this one? How many steps will this mechanism not take? It won't take one. If it took one, the rate law would have to involve both water and the bromide. The rate law here for an SN1 is only going to depend on the concentration of the bromide. Right? The rate law only depends on the concentration of the bromide. Doesn't matter how much water you have here at all. And the other thing is, so this goes from pure R to racemic. All right? So again, a racemic mixture is 50% R, 50% S. Right, so that hydroxide, half the molecules have the hydroxide out at us. I'm calling it a hydroxide. Have the OH out at us, half have it back. So take 2 or 3 minutes here and see if you can come up with a mechanism that explains the rate law and the stereochemistry. And if you get that, try to do the alkene over here. What's your question? Yeah. I drew it as HBr. Here, if you have HBr or HCl or HI or nitric acid, sulfuric acid, if you have those in water, you have H3O plus and the conjugate base, right? So if I have HBr in water, aqueous HBr means I have H3O plus and Br minus. Probably getting hard to read for you guys now. So I've shown you the SN2 mechanism above it. Thing about that SN2 mechanism, the bonds that form and the bonds that break are the same as in the SN1 reaction. Right, so you need a curved arrow for those. Right, so up above, I have a curved arrow from O to the electrophilic carbon. I have a curved arrow from the carbon Br bond to the Br. All right. Question? Okay. All right, so it can't be one step. If it was one step, this rate law wouldn't be right. The rate law would depend on the concentration of water. We're also making H3O+. Like I said, I made this mistake earlier. I'm going to use that as a teachers do that, right? If I make a mistake, it's a chance for me to tell you not to make that mistake. If you make a mistake, it's a deduction. Life ain't fair. All right, so what I did is I mixed up acids and bases. You're never going to have a reaction that's got OH minus in it and H3O plus in it. Similarly, you're never going to have a reaction that's got any strong base and a really strong acid in the same mixture. If you do, they just neutralize each other. All right, so the fact that we get H3O plus out of this, or HBr, means we don't have hydroxide. So a lot of people are going to want to do this, right? Whoop. Don't do that. Protons never spontaneously leap off of atoms. Molecules never just dissociate. A base has to take acidic protons. There's not a base in this reaction strong enough to take this proton off. So that does not happen. All right, so we need to break the carbon-bromide bond. Right, we have to break the carbon-bromide bond, and we have to make a carbon-oxygen bond. Can't be one step because the rate law is wrong. And we can't make the carbon-oxygen bond first. How come? Well, there's that, but there's something else. Right, you'd have to break the CBr bond at the same time. Then it's just an SN2 reaction. All right, I can't make the OC bond without breaking something. All right, so what has to happen first is the bromide leaves. That gives me a carbocation and an alkyl halide, and the bromide ion. And this is going to be the first step for both SN1 and E1. So the first step over here is the same. And now, I hope you can see why SN1 and E1 tends to be slower than E2 and SN2. If you have a really strong base or a good nucleophile around to do SN2 or E2, that's going to happen first because that base is driving the reaction. Here, you're relying on a weak but stable covalent bond to simply break. That's a slow process. All right, so we get this carbocation. Let me draw all the stuff on the carbocation. All right. What's the hybridization of the carbon with the cation on it? It's sp2. What's the shape? What's the geometry of an sp2 carbon? Anybody? Trigonal planar. It's flat. All right. So now the next step. Now we can make the O carbon bond. And again, you do not have hydroxide in this reaction. So you can't have hydroxide attack. This carbocation is a super strong Lewis acid. It's very electron deficient. It really wants electrons. So water, even though water is a weak base and kind of a poor nucleophile, it's perfectly reasonable to have water attack the cation. So water attacks the cation, and again, now we get our stereochemistry. That carbon's flat. Now your orbital, you don't have to do a backside attack. There's no backside. There's a flat front, a flat back. All right, so the water can come from the left, it can come from the right, it can top, bottom, back, front, whatever. But each of those are equally plausible. And again, you don't have hydroxide. So water, the oxygen, one of the lone pairs on the oxygen makes a bond to the carbon. Both of these hydrogens stay there. All right? And now, a hydrogen bonded to a positive oxygen with 3 bonds is really acidic. It's like H3O+. And so now water can take this proton off, and we get our product, and we get our H3O+. Right, so once we get this protonated alcohol, water can take the proton, we get the neutral alcohol and H3O+. In a pinch, I don't really care a whole lot if you use bromide. Like, a lot of people will show this with bromide grabbing that H and you generate HBr. But again, if you make HBr in water, you're going to have H3O+. So the fact that you go through this cation explains the stereochemistry. The water can come from the left, right, front, back, top, bottom. How does it explain the rate law? It does explain the rate law. How does it do that? Right. So we have what's called the rate determining step. Right? If this step determines the rate, then by definition, that's all that's going to appear. I can't draw parentheses all of a sudden. This also is sometimes called a slow step. So basically, the only thing that matters in determining the rate of this reaction is how fast that bromide comes off. Once the bromide comes off, now you have a superreactive carbocation sitting in a sea of nucleophile. Right? Water slamming down on this cation is really fast. Water taking an acidic proton is really fast. So as soon as you get here, the reaction's pretty much done. Like, there's no way you can go in here and like see a large concentration of the cation or the protonated alcohol. Right? So the way kinetics works, every molecule that appears in or before the rate determining step has to appear in the overall rate law. Anything that only comes in after does not. All right, so if there had been 2 or 3 things before this bromide, they would also appear in the rate law. But here, we only have this alkyl bromide in the rate law. And the same is going to be true over here. All right, this first step is the rate determining step. All right, so now last thing for today, I'll give you 30 seconds to draw a mechanism to go from the carbocation to the alkene. Okay, before I give you this mechanism for Thursday, if you're lucky enough to come to class, if not, if you're at home, we will start with this reaction on Thursday. It's the last sort of general thing to talk about. After that, it's going to be me putting reagents up on the board and asking you what you think the products are, what you think the mechanism is, that sort of thing. So that's a little homework. All right, on the mechanism up at the top, the last step here, all right, so we have a carbocation, and again, that carbocation is flat, lobes above, in this case in front and behind the board. And remember, in any carbocation, all right, so here's the shape. That carbocation is being stabilized by a bonding pair on the beta carbons. Right? That beta hydrogen is interacting a little bit here. We looked at that in chapter 6 with cation stability. So the more a tertiary cation is more stable than a secondary, is more stable than a primary. And the reason is this sort of electron donation from a beta whatever bond. Well, if these electrons are being pulled toward this vacant orbital, right, that's a plus, that makes this H really acidic. So now a fairly weak base can take that proton. So water can grab that proton. You neutralize the carbocation by making the pi bond. You do that at the same time. I sometimes will see people draw, a one-step thing, and they'll wind up with a plus and a minus here. What is this a resonance structure of? It's a resonance structure of the product. But it's a really bad resonance structure, right? So don't do that. Go grab the H, and you can get to any of the alkenes by grabbing any of the H's here, except these three. Make the pi bond with the CH electrons, and you're done. So again, that's E1, E2, SN1, SN2, all in general terms. We'll start doing more specific examples next time after this one thing down at the bottom. See some of you in lab here in a few minutes. The rest of you I'll see Thursday or Tuesday, or office hours, or just around town. See it. You can ask a quick question.
With what you just said at the end, the arrow from the water going to that hydrogen,
Uh-huh.
there's still, in actuality, there's two hydrogens.
There are,
You're
yeah,
just saying
yeah.
it's the other one. Okay.
And now you can grab either one. Both hydrogens can lead to cis or trans. Yeah, there's no, for the carbocation is both way more reactive and stereochemically just sort of loose. It can make, you get a racemic mixture, you get diastereomers, and that's a hallmark. SN2 and E2 tend to give like one product, or a stereochemic, this stereoisomer turns into that stereoisomer. SN2, you always get inversion. SN1, you always get racemization. E1, you always get like a buttload of products. Yeah. What's up?
So for the bulky base, yielding more Hoffman product, is that just for E2 or is that E1 as well?
E2.
Just
E1, like, you bet. E1, you can't have a strong base. If you have a strong base, it's going to be E2.
Okay.
So with E1, you make the cation, and now just like any base can come in, grab any hydrogen.
Okay, so if
Any of those hydrogens can get, it's going to be regioisomers. Like the two here, like either one of those protons can give cis or trans 2-butene.
Yeah, I guess what I'm asking is, you said like the bulky base yields more Hoffman product for the E2.
No,
E1, it doesn't matter.
for E1, the Zaitsev product, the most stable alkene, because it's actually reversible, right? If you think about it, so we get an alkene and HBr. Chapter 8, right? If I have H3 plus and an alkene, I go back. So you get this equilibration, and you tend to get the more stable alkene
Okay,
always.
and then my second quick question, since we're talking about rate laws for an acid-base reaction, this came up when I was working on the final problem set, is depending on which side is favored, does that change what the rate determining step is?
There's only one step.
It's the reactants products.
Well, there's also products. So the rate
That's what I'm asking.
the rate law for reactants to products is K times the concentration of each reactant.
Mm-hmm.
The rate law for products to reactants is some other K times the concentration of the two
And
reagents.
the fast step would be whichever is from going towards the favorite is the fast.
Yeah, going toward the favor is faster. So the equilibrium constant for any process is also, so another way to think about this, right? If I have, so acid base is good. At equilibrium, the rate from left to right is the same, right? Any one molecule is going, sometimes it's on the left, sometimes it's on the right. But overall, the concentrations left and right stay the same.
Okay.
And so what that means is, if the left to right is faster than right to left, you're going to have more stuff on the right.
Yeah.
And the faster reaction gives you which one's predominant.
Okay, thanks.
Yep.
I just want to let you know I left my laptop and my goggles in the room, so I might be a little late.
When do you get this off?
In a week,
Like it will be off a week from now?
hopefully, yeah.
Because if you wanted to just swap out and come next week, you could. Either way. Go get your lab coat, though. If you're coming today, go get your lab coat right now.
I'll just go today.
All right, see ya.